This is a presentation about MRI geometric distortion reduction. My name is Stephen Jackson. I'm an MRI physicist at the Christie in Manchester. So we'll look at the causes of geometric distortion and some examples, and then we'll look at some specifics for cochlear implants and then some pulse sequence alterations that can be made to minimize the impact of the cochlear implant on the images. The first cause of MRI geometric distortion we'll discuss is magnetic field inhomogeneity. The 1.5 Tesla scanner will be 1.5 Tesla in strength at isocenter, and actually it'll be 1.5 Tesla to within 1 part per million across a 50 centimeter diameter spherical volume around isocenter. So the hardware is such that it will have a very homogeneous field in the center of the ball. As soon as the patient goes in, that will be affected, but then shimming will happen that will reduce the effect of the patient on the field inhomogeneity. Metallic objects can have an effect on the field homogeneity. They can either add or subtract to the field depending on whether they are diamagnetic or ferromagnetic in construction, and this can have a significant effect on the homogeneity of the magnetic field. The second main cause of geometric distortion in MRI is gradient nonlinearity. On the left-hand side, we have an example of all the different gradient coils that are under the bore of the scanner that provide the gradients in the X, Y, and Z direction as shown. In an ideal world, when current is put through these coils, a completely linear gradient will be applied across the patient, as shown in the top left. In the real world, however, that ideal gradient of a complete straight line from top to bottom of your field of view isn't exactly replicated by the hardware, and actually the gradients do tail off a little bit at either end of the field of view, and this can cause, or this does cause, some geometric distortion. So during the scanner commissioning, the gradients will be calibrated such that the signals received are mapped to the correct spatial dimensions. On top of that, some manufacturers have a distortion correction post-processing option available that allows you to account for these changes in the gradients even more subtly, and this should be enabled wherever possible, especially when dealing with cochlear implants. So we'll now look at some examples of MRI geometric distortion. For the first patient, they were scanned with their head a little bit too far away from isocenter, and that resulted in their craniocaudal dimensions of the head being reduced compared to the CT, and this meant the patient had to be rescanned for their radiotherapy planning scan. The second patient, during the commissioning, it was noticed that the scanner gradients had been miscalibrated, so we have a scan of a particular patient before and after these gradients were miscalibrated, and you can see a significant change in the geometric appearance of the patient's head. Third example is a classic example of a patient with lots and lots of hairpins in, and you can see that they've had a significant impact on the local magnetic field, and that's resulted in the characteristic metallic artifact that has a geometric component to it. And in the bottom right, we have an example of a gradient nonlinearity distortion correction. The right-hand panel is the sequence with no 3D distortion correction applied, and the left-hand panel shows the image reconstructed with 3D distortion correction applied. And you can see the location of this lesion here in this MPUH sequence has been altered by that distortion correction algorithm. So now move on to discussing some cochlear implant specific information. The susceptibility of the implanted magnet and the cassette around it causes nearby hydrogen spins to experience different magnetic fields than intended during the spatial encoding process. And this leads to characteristic geometric distortion, signal voids, and signal pileups. We can use standard techniques to reduce these artifacts around metal implants, but we cannot remove them completely. I refer you to a paper from 2018 from Edmondson et al., which discusses reducing artifacts near highly inhomogeneous magnetic fields. In the top left, there's a sagittal T1 image, and you can see this information has been mapped into the slice of interest from adjacent slices. In the top middle is an axial T2 flare image, and we can see a characteristic artifact around the implant site. The top right is a gradient echo sequence, and this characteristic signal void artifact is far greater on the gradient echo sequence than it is on the turbo spin echo examples. The reason for this is the turbo spin echo has a characteristic 180-degree refocusing pulses that allow some of the magnetic field inhomogeneities to be undone. In the bottom left is a diffusion-weighted imaging sequence, which is essentially undiagnostic. The reason for this is that the EPI sequence has an extremely low bandwidth, and we'll discuss the importance of bandwidth in relation to metal artifact reduction in upcoming slides. The last two panels show an axial T2 FATSAT sequence, with the magnet implanted in the middle panel and explanted, but with the magnet cassette still in situ on the final panel. And this shows that the contribution to the artifact from cochlear implants is not just from the actual magnet, it's from the cassette as well. So firstly, the geometric distortion. If you, by applying the slice gradient across a patient and inputting RF at a certain frequency, you would expect to be able to excite a single slice of tissue. However, in the presence of a metal object, that will affect the local field such that the resonant frequency of spins is not as intended in the desired situation, and information from other slices will get mapped into the slice that you wish to excite, and information from the slice that you wish to excite won't be mapped in at all. And this can lead to a non-linear slice profile such as this. So that accounts for some of the geometric distortion. You may also experience signal void. If the presence of the metal is such that it affects the resonant frequency significantly, then actually not only will there be no signal from the nearby spin that you want to excite in the slice of interest, but also that all the spins in the slices nearby will be so far away from the resonant frequency of the input RF that they will also be missing as well. And this can lead to a significant signal void in the image, which obviously you're very familiar with from scanning cochlear implants. So the actual result of this will be a complete void in the image. Finally, signal pileup. If the slice gradient is applied and RF is input, you would expect to only excite the slice in yellow here. However, if there's a metal object close to spins in a nearby slice, that could alter their resonant frequency such that the input RF will also resonate with those spins, and they will be actually translated into the image. Because they existed at a different location in the slice encode gradient, they will also be spatially misregistered in the final image. And this will lead to a significant pileup of signal in, for example, in this gigantic pixel here, we'll have spin information from both this spin and the extra one that's being mapped into the plane, and this will result in a signal pileup. So let's have a look at this in a phantom. So on the top left, we have a cochlear implant phantom that was commissioned locally. You can see a white perspex sheet running through the middle of it, and on that sheet there's a location where a cochlear implant magnet can be installed, and it's surrounded by MR signal generating fluid. And the results of a sequence being run on this scanner and then the slices being cycled through is shown here. So the black line is that perspex sheet, and you can see as you move through the slices and we get closer to the implant, there's a significant amount of geometric distortion experienced by that perspex sheet. Further, the signal void is glaringly obvious throughout, and similarly the signal pileup, which is this extremely bright region of all these extra bright pixels here, is characteristic. So we'll now discuss the pulse sequence adjustments that can be made to minimize this distortion. The main aim is to reduce the amount of time that spins have to dephase due to the presence of the magnetic field of the implant. So the very simple ones, it's advised to use turbo spin echo sequences instead of gradient echo sequences. Again, that's because they have this 180-degree refocusing pulse that can undo some of the damage of magnetic field inhomogeneities locally. It's also advised to minimize echo time and echo spacing for TSE sequences. And for some manufacturers, this is possible to do by enabling the faster gradient option. Reducing slice thickness will reduce the severity of the artifact. And finally, increasing receive bandwidth will also reduce the effective susceptibility, and we'll discuss that very soon. It's very important to note that both SNR and SAR will be affected by making changes such as these. So as a simple example of this, we'll look at NF2 head scanning at MFT. There is a routine NF2 head protocol, and then there's an adapted protocol for NF2 heads with cochlear implants in situ. There is a T2 turbo spin echo in the trans orientation, that's the same throughout. There's a T1 SE trans with FATSAT in the routine protocol, and the FATSAT is not applied in the cochlear implant protocol. There is a T1 3D gradient echo sequence in the routine protocol, and that is replaced with a T1 spin echo 2D sequence coronally in the cochlear implant. So we can see there's been some changes made here. Firstly, spin echo is used instead of gradient echo because we know the artifact for gradient echo sequences is far more severe. The TE is set to minimum throughout, actually in both protocols. 3mm slices are employed. This is quite low and lower than some others in non-NF2 protocols. Distortion correction is on where it is available, and it's advised to avoid spectral FATSAT for scanning with severe metal artifact, for reasons we can show in a upcoming slide. And this again has been adhered to in the difference between the FATSAT on the routine NF2 protocol and the lack of FATSAT on the same protocol for cochlear implants. There are many cochlear implant patients not on the NF2 pathway, and these may require a wider range of pulse sequences in the brain. The left panel shows the results of a 3D Fiesta sequence, also known as a TrueFISP or a balanced FFE. These are gradient echo sequences, and that results in a significant signal void. But also, because of the nature of the pulse sequence, there are many banded fringes that radiate away from the implant that can potentially hinder diagnostic ability for these sequences. The second panel shows a turbospin echo sequence with FATSAT applied. See the extent of the original void from the implant, but then there's a second band of signal void potentially related to the FATSAT pulse. And the final slide shows the results of a stir sequence coronally with the cochlear implant magnet in situ on an adjacent slice. The actual geometric fidelity within the plane of the image is quite good itself, but you do get an extra copy of some brain anatomy in the top left of the image for free, which is quite unusual in appearance and may give uncertainty about diagnosing any pathology up in this region of the image. We mentioned earlier that increasing the received bandwidth can have a positive impact on the artifact from the cochlear implant. We'll just discuss this in a bit more detail in the following slides. So received bandwidth is related to the strength of the frequency encode gradient. GE report their received bandwidth in kilohertz, and that is the size of the frequency difference due to the applied magnetic field gradient across the field of view in the readout or frequency encode direction. Siemens published their received bandwidth as frequency per pixel, so it will take the entire frequency change across the field of view in the readout direction and divide it by the matrix size in that direction to give a value in hertz per pixel. Philips have a different approach whereby the known 220 hertz difference in resonant frequency between fat and water tissues at 1.5 T leads to the chemical shift artifact in the frequency encode direction, which causes a spatial misregistration of fat and water tissues. This known 220 hertz chemical shift difference can be divided by the Siemens stated hertz per pixel, leaving a number of pixels by which the water and the fat tissues are misregistered in the final image, and this is referred to as a water-fat shift. It's important to note that if you increase the bandwidth, then the SNR will decrease as a result, and the SAR, the SAR, will be unaffected. We'll now have a look at the effect of adjusting received bandwidth. We suspect this will have an effect because if a metallic object contributes a certain amount of inhomogeneity to the B0 field, then increasing the received bandwidth will distribute this effect across fewer pixels. And we can see this on the following slides. We have an example of a phantom with a cochlear implant in situ and a received bandwidth of 191 hertz per pixel. You can see around this auditory implant there's some significant geometric distortion appearing in the top right of the phantom. If we increase the received bandwidth to 500 hertz per pixel and accept the accompanying decrease in signal to noise, we can see that this geometric distortion has been reduced significantly. We further increase the received bandwidth, then the geometric distortion improves again. However, the signal to noise drops further. And there's more changes we can make, for example, by leaving the received bandwidth at a very high level, but also increasing the matrix size from 256 to 512, and increasing the echo train length of this turbospin echo sequence from 16 to 24, we'll get an image that has got really rather good geometric fidelity. The signal void artifact is minimized. However, making all of these changes will result in a very low SNR. So this image was obtained with a number of signal averages or averages of 4, and this means the acquisition time has jumped through the roof. And more echoes in your train and a higher matrix size will lead to a higher SAR pulse sequence. One final option is to use a specific metal artifact reduction sequence. So on the left, we have an example of a slice encoding metal artifact correction sequence, or CMAC. On the left, we have the same phantom that we met before with the spin echo sequence. And these sequences can be extremely effective. Unfortunately, they take a long time and they're very high SAR. However, very recently, a compressed sensing version of CMAC has become available on Siemens scanners, and this will reduce the acquisition time and SAR considerably where it is available. I mentioned SAR multiple times throughout. The vast majority of pulse sequence changes you will make will have an impact on the SAR. And unfortunately, the different manufacturers have got different SAR limits for each of their devices. These are summarized in this local document here, and it is important to be always checking the SAR when the patients are being scanned to make sure that these limits are met for all of the different devices. So to summarize, geometric distortion is an intrinsic feature of MRI. Software and hardware solutions exist to minimize this as much as possible. Cochlear implants generate significant artifacts due to their magnetic susceptibility. However, pulse sequences can be optimized to reduce these artifacts. They can't be removed, but they can be reduced. However, when making pulse sequence optimization changes, you need to be aware of the impact on SNR and SAR and these changes. Thank you very much for listening. If you have any questions or comments about the presentation, feel free to contact the-christie.mrphysics@nhs.net.